Are you ready?
Yeah.
Time.
Hello, we're Green Biofuelers. I'm Milton Diaz, Gini Fernandez, Luis Perez, and we'll present to you our senior design project, which is the design of a biodiesel feedstock pretreatment station. This is our outline. Our sponsor, Green Biofuels, they're a newcomer to the South Florida energy market. They bring their biodiesel experience from Brazil. They lead the local biodiesel production. Green Biofuels lacks the medium of thoroughly removing water and debris from the waste vegetable oil they use for biodiesel production. This makes them highly dependent on purchasing high-priced, already cleaned waste vegetable oil. Our objectives: design, analyze, and assemble a waste vegetable oil cleaning station, follow operational safety and pro-governmental regulations, and produce the highest quality of feedstock possible. Biodiesel, a fuel made from vegetable oil and animal fats. It's got similar combustion properties as fossil fuels. An interesting fact, Rudolf Diesel's main engine model was first run with vegetable oil. In remembrance of this occasion, which was the 10th of August, the International Day for Biodiesel was made this day. Why biodiesel? Lower emissions than fossil fuels, it biodegrades easier, it's less expensive. These are some of the trends of biodiesel in the US, biodiesel production in the US in the last decade. Biodiesel feedstock is comprised in virgin vegetable oil and waste organic oil. In this case, it's seen in grease traps, animal fats, yellow and brown grease. Biodiesel, it's also the feedstock. It's also classified in its free fatty acid content, the sulfur percentage, the cetane value, and of course the water and debris content which it has. Our main goal of this project is to reduce yellow grease and brown grease water and debris content from 1,000 ppm or less for water and to 5,000 ppm or less for debris. Most biofuel processing plants follow the sequence of treatment. The waste vegetable oil goes through a transesterification process, then hot wash process takes place, then it's hot dried, then the biodiesel is produced. This is a exploded partition of our proposed design. The waste vegetable oil will go through a filter screen into a cementation tank where it will be increased in temperature. This increase in temperature will accelerate the sedimentation process. Then the transfer pump will send the oil to the centrifuge, then through the filter membrane, and then it will be ready to be processed in the biodiesel plant.
This is a three-dimensional render of our prototype. To build the plant, we had to get data from Green Biofuels. They gave us the tank capacity of 1,800 liters per hour. We applied a standard velocity of fluid, and we reduced the flow rate of the prototype by 10%, and also the size we reduced it by 10%. And we applied fluid properties of water for our calculation. We also calculated a pipe diameter with this formula, and from that diameter we set it to 1/2 inch due to easy availability, and we also rearranged the formula to acquire new velocity, and we also calculated the Reynolds number, and we had a turbulent Reynolds number. We then used the Reynolds number and the smooth curve from the Moody diagram to obtain our friction factor. We also calculated the major losses in the pipes due to friction. This sketch presents the first design that we made, which the centrifuge had the option of being bypassed. To calculate the minor losses, we listed in this table all the types of feedings we used, the loss coefficients, the quantities, and the formula we needed to calculate the minor losses. We also acquired the minor losses that were given to us by the manufacturer.
Excuse me, back there. Thank you.
We use the formula to acquire the head loss, and then we use this equation to add up the entire total head loss, which was 63.2 feet. To obtain the total system head, we use the modified Bernoulli equation, applying these assumptions, and we obtain a system head of 61.85 feet. We then use the volumetric flow rate, the design volumetric flow rate, and from a range from 0 to 200%, and to generate a range for our system curve.
After that, we're ready to select pump. These are our 6 candidates for our pump selection. This is a graph of the system head and the volumetric flow of the 6 candidates of pump candidates, and the system curve. It's the blue one in the middle. These are the two candidates that best approach our operating point. Then we proceeded to correct our viscosity. This is viscosity chart we use to correct the viscosity between oil and water. Once we got it corrected, we got new values for our volumetric flow rate and our total head. And we selected the pump that was closer to our operating point here. It's a overduffer centrifugal high-speed pump. It pumps up to 2 gallons per minute. After we selected the pump, we did analysis to prevent cavitation inside the pump. We made to make sure the pump was operating in a safe range. We made sure that the available net positive suction head exceeded the required net positive suction head in order to operate in a safe range.
After selecting the pump, we then focused on the other 4 major components for the prototype. The sedimentation tank, where most of the debris and water is removed. We manufactured the sedimentation tank ourselves by modifying a cylindrical container. We braced some fittings and adapters and a ramp inside the tank in order to facilitate the sediments to go to the bottom. We simulated the fluid behavior inside the tank through the suction port. Also, the heater element, another important component. It puts out 1500 watt. It has a variable thermostat with a dial knob. This is a scale reading of a dial with the temperature reference. And the centrifuge, possibly our second most important component, water remover component after the sedimentation tank. The centrifuge, when we acquired it, we noticed that in order for us to install it inline the prototype, we had to manufacture or modify its outlet, which we did. We manufactured ourselves. And finally, the other major component, the filter membrane, which is the main debris remover in the prototype after, again, the sedimentation tank. Having together all these major components, we rearranged the system flow to where the filter membrane will be the one with the option of bypassing, and the centrifuge will always be inline. This is the system curve together with the pump performance curve for the new system. After acquiring the centrifuge, and as we went to install it inline to the prototype, we noticed that placing it inline of a pipeline will create a backflow inside towards the same centrifuge. This would affect the cleaning ability of the centrifuge. In order to fix this, we decided to rearrange the system again, splitting the system where the pump will send the fluid, and through using a 3-way valve, we will split the system to one cycle going to the centrifuge and another cycle to the filter membrane.
This graph shows the final pump performance curves. This is the filter membrane cycle system curve. This is the centrifuge cycle system curve, and they're in relation to the plastic centrifugal pump curve. These are operating values. We chose the maximum flow rate for our operating parameters. We also did a heat transfer calculations. We determined there was going to be heat flow rate from the tank to the installation of 4.75 BTUs per hour, and the energy loss will be less than 10%. We built a control panel in order to operate the pump and the heating element more efficiently and safely. This is the electrical circuit schematic of the control panel. Some complementary parts include the three-way valve and the primary filter, and also we have the power platform seen here where most of the components were assembled, and we also have the metal screen which goes inside the centrifuge, the cementation tank, and that's where we first pour our feedstock. We also had leveling supports as seen right here. This is to keep the elevation of the outlet ports in the same level as the outlet of the cementation tank. And finally, this is our prototype, which we can see here.
In the biodiesel industry, there are several types of testing for water. As you can see, we listed some of them here. But the one that we use in our prototype was the Sandy Broad water test kit. It's more accurate, and it was better for our increase the accuracy of our results. For the water testing, before we pre-treated the feedstock. The yellow grease, for example, had 16,000 parts per million, and after a cycle in the system, we reduced it to 1,000 parts per million on the water content. For the debris content, we use the weight filter weight method. We filter a liter of clean oil, and then we filter a liter of dirty oil, and we measure the difference. And with this relation of mass and volume, we came up with we obtained the part per million of debris in the feedstock. As you can see, to pick one brown grease, before we run it through the debris system, we had 35,000 parts per million of debris, and after 3 cycles in the mixer and in the filter membrane, it was reduced to 4,705 parts per million. This is our final cost analysis. Everything sum up to $1,100 average. This is our timeline. As you can see, we spend most of the time in the material acquisition and in the final prototype development. For safety, we increase the safety in our system by all the heat elements were insulated. Every electrical component was connected to a circuit breaker. We have a MSDS data sheet, and all the values in our feedstock quality was in the proposed values that we begin with. There is a summit in Asia, the Asian Pacific Clean Energy Summit. It was this past semester, but this is just to show that the clean energy is a global necessity, and there are opportunities to expand this project, bring it outside the FIU, outside the United States. And we want to thank Dr. Tremante and Javier Palencia, and the FIU engineering faculty. GreenBiofuelers, which was our sponsor, and Mr. Masenko helped us get some supplies for the system. This is a quick video of the system operating, which was,
sediments are removed from sedimentation tank to the bottom. Oil has been in the sedimentation tank for quite a while now. Temperature ranging in the 160 degrees Fahrenheit, tank temperature 130, insulation temperature at room temperature 70 degrees. Centrifuge cycle. Valve open.
we're going to move it forward because of time. More or less to the liquid zone.
Reset. Aligning for filter membrane cycle.
The first one was the centrifugation. Now we're gonna run
Starting
through the
pump.
filter membrane.
Primary filter. Pump. Inlet valve. Filter. Secondary filter.
This is the pipe to the left. And that's our presentation.
Okay. Questions? Dr. Basil is back.
Question here. I missed the first half. Can you do it again?
Our pleasure.
Dr. Tremonti?
What is it that's unique about this design?
Unique. For us, everything is new. We're students. Unique about this design, it will benefit the biofuel, the company greatly because it will reduce the cost in maintenance they have inside the plant. They have already some problems with some components got damaged because they didn't pretreat their feedstock, and also they didn't have a way to test, but they didn't test the feedstock before they acquired it. They didn't have a way to. They were not, since as long as we don't know, they didn't have a way to classify the feedstock. This prototype might help develop that in the company.
Actually, also they were trying to get into more a greater type of availability of feedstock. They were only, like we said in the beginning, they were only dependent on purchasing waste vegetable oil, which was already pre-cleaned, which in this day and age, cooking oil, as hard as you may think, it's gotten expensive. The residual cooking oil, people are actually collecting it and using it and selling it to biodiesel producers for, you know. So Green Biofuels didn't have that. Well, they still don't have that pre-cleaning station in order to be able to acquire any type of oil, not mattering if it was 0.5% of it in water or debris, and to be able to put it in their plant for processing. So.
When we first got there, just for example, they were just having problems because they purchased a big amount of what they thought was waste oil, and most of it, more than half was water, and they lost a lot of money. Any other questions?
There is something we comment that usually in the oil industry you separate liquid, which is oil and water. I use big tanks using gravity. You have to have time, waiting 8 hours, something like that. So in here you don't have that. So the real added value is dynamic components without using static components, which are too big, and you need it's time consuming, and also you need space where maybe here you don't have it. And like they said, water is not the component they're looking for. So solid is one thing, gas could be something else, but here the main thing is separate liquid, which is the same thing. That's maybe the real added value behind all this.
Thank you.
Were you through, Dr. Tremonti?
The second question pathway is scale up, obviously. How would you scale this up? And what about the waste paths? Like the water coming out of the system, what do you have to do with that water? Is that water usable in its form?
Well, for scale, this is just the first the first part of our design, a small prototype. Obviously, in the near future, I don't know if maybe they like to fund a bigger scale design, like close to this one. Obviously, you wouldn't have the two platforms. It would be straight. They already have the tanks actually, and I think they might be already using. They didn't wait for us. They might be already using another method of cleaning. I think it's bacterial cleaning, which I know a lot of water plants use. But you never know. Maybe just this is a very practical way of just removing big amounts of water and debris. Like the results show, the brown grease, we took it down to less than 5,000 ppm, which was the preset conditions.
It's what the ASCM needs to. This is basically the law of biodiesel. Have some regulations, and one of the regulations says that it should be below 5,000 parts per million, and we achieved that goal.
Okay, thank you.
All right, my question, I have 2 or 3 questions. What percentage of your feedstock is likely to be found from grease traps?
Well, go back to the classification. This one. No. From you said grease traps.
Yes.
Well, the two type of feedstocks we tested in the prototype were yellow grease and brown grease. Grease traps are the debris. For example, debris content might be in the 90% of debris or 80% of debris. Brown grease oscillates sometimes it's like half, like 50%. It's let's say garbage, and the oil is oil. And the oil is oil. So for grease traps, I imagine that 30%, 20% of it would be, or maybe less, 10% maybe would be usable oil.
But there's no way to tell because every grease trap is different. It have all type of debris in there. What we know for sure is the amount that it needs to have to be processed. But all grease traps, like I said, one shipment came from China. We have all the tank was water. Another one might be richer in
Free fatty acids.
the feedstock to get better quality of biodiesel.
Okay. For your project here, what was the division of labor? I didn't see an accurate breakdown of who did what and how much was that?
It was spread evenly. We all put in with the report, with obviously assembly of the component. Even though we did call GreenBiofuels our sponsor, we actually funded the prototype ourselves, so we split the cost evenly. The labor, the analysis, the testing, the weeks of testing after we were able to assemble the whole prototype.
Okay. And how effectively did you address the global issues, global components?
Well, GreenBiofuels is.
Do you have a slide on that?
GreenBiofuels, it is a newcomer to South Florida. They just recently moved up here from Brazil.
Clean energy is a global necessity. I mean, maybe these people, GreenBiofuels came from Brazil, but this is all over the world. Like you see, this summit, for example, is in Asia. So anything that has to be related to clean energy, I think is a matter of the whole world.
It is a summit that we're trying to, but I mean, being budget-wise, I mean, it's not going to be in Hawaii. It's probably going to be in another oceanic or Asian nation. So it most probably won't be able to assist. But when we first started the project, we did have some strong thoughts of at least, maybe participating in the Brazil one, but
Okay. Are there any other questions? Dr. Basil? No? All right, well, thank you.